Welcome back to The Deep Dive. Today, we're pulling back the curtain on a realm that, well, it still feels like it belongs in a sci-fi novel, but is very much taking shape right now, quantum computing. Our mission for you, our listener, is basically to cut through the jargon, illuminate the why, and, clarify what this incredible technology actually means for our future.
Yeah.
We're going to navigate the bizarre rules of quantum mechanics, right? From qubits and superposition to entanglement and error correction.
All the greatest hits.
Exactly. And even explore how these machines could one day challenge today's, well, most robust encryption. And here's the best part. No physics degree required.
It's a truly fascinating subject because quantum computing really challenges every intuitive notion we have about how information is processed. It's built on a foundation of rules so counterintuitive they were once called spooky.
Right, spooky.
But those very rules, they unlock a fundamentally new way to compute.
Absolutely. So, okay, to really grasp the quantum leap, let's maybe quickly ground ourselves in the familiar. Think about the computers you use every day, classical machines.
Yeah, the standard ones.
At their heart, they operate with bits, right? Those tiny electrical switches that are always in one of two states, a 0 or 1. It's either on or off. Basically, a simple binary decision. Every email, every video, every calculation on your phone is built from billions of these simple choices.
And this binary approach it's incredibly powerful. Even our fastest supercomputers, with trillions of these tiny switches, they excel at sequential tasks.
Yeah.
They can perform operations one after another with just astonishing speed.
Right.
Yet even with all that power, they hit fundamental limits when faced with problems like, say, perfectly simulating complex chemical reactions or factoring enormous numbers. They're kind of like a super fast car that still has to drive every single inch of the road.
That's a great analogy. Right, and the ingenious part of classical computing for decades has been shrinking those transistors, those tiny switches, down to like microscopic levels.
Smaller and smaller.
The more you pack in, the faster it gets. We even have a brilliant blueprint, the von Neumann model, where programs and data live side by side. But as we continue to miniaturize, we're bumping up against the very laws of physics.
Yeah.
We're reaching a point where classical physics just isn't quite enough anymore.
It's like trying to make your car go infinitely fast.
Yeah.
Eventually, you just can't put a bigger engine in. You actually need a whole new mode of transportation.
Right.
So when bits simply aren't enough to describe the complexity of the universe, we have to ask, what comes next?
And that next is where quantum computing steps in, offering a completely different paradigm for processing information. Instead of classical bits, we have qubits, quantum bits. And here's where it gets truly mind-bending. Unlike a bit that's either 0 or 1, a qubit can be both 0 and 1 simultaneously. This incredible property is called superposition.
Yeah, superposition. A great analogy for it is maybe like a coin spinning in the air.
Okay.
While it's spinning, it's not heads or tails, right? It's a dynamic blend of both possibilities. Only when it lands, or you catch it, does it resolve into a definite state.
I see.
Qubits behave in a similar way, and this is really where the exponential power starts to emerge.
Exactly. So with a classical bit, you've got two possible states. With two classical bits, okay, you have 4.
Right.
But with 2 qubits in superposition, you're not just dealing with 4 separate states, you're dealing with all 4 states at the same time.
All at once.
And this scales dramatically.
Yeah.
Add another qubit, and you double the possibilities again. Just, 20 qubits can represent over 1 million states simultaneously?
Over 1 million, yeah. It's like having, 1 million parallel universes where every possibility exists at once. It's mind-boggling when you think about it.
It really is.
And that's before we even get into entanglement.
Oh, right, entanglement.
If superposition is like that single coin spinning, entanglement is like 2 or more coins that become so deeply linked, so perfectly correlated,
Okay.
that the state of one instantly tells you something about the state of the other, no matter how far apart they are.
Wow.
Einstein famously called it spooky action at a distance.
Spooky action at a distance.
Ow.
I mean, that just sounds like science fiction, but this is a rigorously verified phenomenon, right?
Oh, absolutely.
Yeah.
Verified many, many times. It's real.
Okay, so these qubits sound abstract, maybe like something out of a textbook, but they're actually built from very real physical systems, aren't they? What are we actually talking about when we say qubit in the lab?
Yeah, that's a really important clarification. A qubit isn't just a concept. It's a delicate physical system. Think of it as maybe a particle or an energy state that we can control and manipulate.
Okay.
And the thing is, there isn't just one way to build them. Each approach comes with its own unique set of engineering challenges and advantages.
So what are some of the leading contenders then in this race to build a practical qubit?
Well, two of the most prominent approaches right now are superconducting qubits and trapped ions.
Okay, superconducting, like circuits.
Exactly.
Yeah.
Companies like IBM and Google are heavily invested in these. They use tiny electrical circuits cooled down to near absolute zero, colder than deep space.
Wow.
These are incredibly fast and show great promise for scalability, but they're also exceptionally sensitive to any kind of environmental noise, which can cause errors. Very touchy.
Noise, like vibrations or something.
Yeah, or stray electromagnetic fields, heat, anything really.
Okay, and the other one, trapped ions.
Right, trapped ions. This approach is used by companies like IonQ and Quantinuum. Here, you're actually suspending individual atoms, ions, in electromagnetic fields using powerful lasers to hold them and manipulate them.
So actual atoms held by lasers.
Yeah. These qubits boast incredibly high accuracy and can maintain their quantum states for longer, which makes them very reliable. The trade-off is often that they are, well, slower to operate. And scaling them up to very large numbers presents different engineering hurdles than superconducting circuits.
It really sounds like a delicate dance, trying to balance speed, accuracy, scalability.
It absolutely is.
And this brings up a crucial point. If these systems are so delicate, and if a qubit can be in multiple states at once, what happens when we try to, look at it? We can't just copy a qubit like we copy a classical bit, can we?
That's a profound challenge. And you've really hit on a core principle, the no cloning theorem.
No cloning.
Simply put, we cannot perfectly copy an unknown quantum state. If you try to observe a qubit to see if it's 0 or 1, you actually force it to pick a side. You collapse its superposition. It's like trying to observe that spinning coin without it landing. The very act of measuring changes its state fundamentally.
So, okay, if we can't just copy a qubit to make a backup or check it easily, that sounds like a huge problem for preventing errors or even just securing information. How do we even begin to work with such a delicate system without constantly breaking it?
It's a critical question, absolutely. And it's exactly why quantum error correction is one of the most active and, frankly, challenging areas of research right now.
Right.
But before we maybe dive fully into error correction, let's really cement what superposition and entanglement do for computation.
Right.
We've described them, but what's their true magic for actually solving problems?
Yeah, good idea. Let's revisit that spinning coin analogy. With classical bits, you're essentially running one calculation at a time, step by step.
Sequentially.
With superposition, though, it's like having, a million coins spinning, each representing a different potential answer, and the quantum computer can sort of explore all those possibilities simultaneously.
Exactly.
And the truly revolutionary part, as I understand it, is that you can program these qubits to create interference patterns.
Precisely. It's like orchestrating waves, You can make them constructively interfere in certain directions, basically amplifying the probability of getting the right answer and destructively interfere elsewhere, canceling out the probabilities of getting the wrong ones.
Okay, so you're kind of guiding it towards the solution.
You're guiding the probabilities.
Yeah.
And then with entanglement, you're not just running calculations in parallel, you're creating these deeply interconnected relationships between qubits. That allows them to process information in ways that are entirely non-classical. It lets quantum computers build these highly complex, correlated computations that can efficiently navigate massive solution spaces. It's not just faster, it's a fundamentally different way of thinking about computation, moving way beyond that sequential binary logic.
It really is a different beast altogether. And these quantum computers, obviously, they don't run Windows or Mac OS.
Not yet, anyway.
Right. They run special quantum algorithms built from quantum gates. So what do these gates actually do? How are they different from the simple AND or R and NOT gates we know in classical computing?
Yeah, classical gates are like simple switches, right? They flip a bit from 0 to 1 or combine two bits in a straightforward way. Quantum gates are, well, they're far more sophisticated. They don't just flip states, they rotate qubits within their quantum space.
Rotate.
Yeah, like changing the probabilities of them being 0 or 1. And crucially, they can entangle qubits or disentangle them. They manipulate the quantum state itself.
Okay, can you give us maybe a couple examples? What would a basic quantum gate look like in action?
Sure. One really fundamental one is the Hadamard gate. If you apply it to a qubit that's initially a definite zero, what we call its Ket 0 state.
That's 0, right?
It puts that qubit into a perfect superposition. It's now exactly 50% years away in its Ket 1 state. So it's not a flip, but a push into this probabilistic blend.
Ah, okay. It creates the superposition. It's a key way to create it, yes. Then there's the CNOT gate, or controlled knot. This one is absolutely critical for entanglement. It acts on 2 qubits. It flips the state of the second qubit only if the control qubit, is in a specific state, usually 1
I see, so it's conditional.
Exactly. This conditional operation is what creates those spooky correlations, that entanglement between qubits.
So these gates are the building blocks then, and sequences of them form these powerful quantum algorithms. This is where things like Shor's algorithm come into play, right? The one that can factor huge numbers much, much faster than any classical computer. That's the one that cryptographers are particularly concerned about.
That's the big one, yes. Shor's algorithm, once we can run it on a large enough stable quantum computer, could theoretically break the public key encryption that secures so much of our internet communication today. Things like RSA.
And another really famous one is Grover's algorithm. It doesn't offer quite the exponential speedup of Shor's for its task, but it dramatically speeds up unstructured search problems like finding a specific item in a massive unsorted database.
Okay.
Both of these algorithms and others fundamentally leverage superposition and entanglement to explore vast possibilities simultaneously, turning what would be like a needle in a haystack search for a classical computer into something far more efficient.
Okay, now, for the million-dollar question, maybe the billion-dollar question. Is this all still theoretical stuff in labs, or are actual quantum computers out there running right now? Because that's where it gets truly compelling for you, our listener.
Right. And the exciting news is, we are absolutely no longer in the realm of pure theory. Not at all. Real quantum processors exist today.
Really?
Yes, and many are even accessible through the cloud. Companies like IBM, Google, Amazon, Microsoft, they all have quantum efforts.
Yeah.
And then you have innovative startups like IonQ, Quantinuum, Xanadu. They're all actively building and refining these machines.
So wait, we can actually log on somewhere and run quantum experiments from our regular computers?
You can. Many platforms offer cloud access. IBM Quantum Experience was one of the first. Amazon Bracket, Microsoft Azure Quantum. They let researchers, and even the public to some extent, run algorithms on real quantum hardware.
That's incredible. So what's the state of the art right now? How powerful are these machines?
Well, it's advancing fast. IBM, for instance, has a very public and ambitious roadmap. They're aiming for fault-tolerant machines with, thousands of logical qubits before 2030. Google made headlines a few years back with its Sycamore processor achieving that quantum supremacy claim.
We'll get back to that one.
Yeah. And IonQ continues to advance its trapped ion systems, pushing qubit counts and quality. Xanadu is working on photonics. There are many different approaches being pursued. However, it's really crucial to understand that these machines are still very much in what we call the NISQ era.
NISQ, right. You mentioned that. Noisy intermediate scale quantum.
Exactly. Noisy is the key word there.
So that sounds fragile. What does that mean for the computations they can actually do?
It means they are incredibly delicate, incredibly sensitive to their environment. Remember we talked about environmental noise?
Yeah. Vibrations, heat.
Even tiny vibrations, stray electromagnetic waves, maybe a cosmic ray hitting the chip, or a slight temperature fluctuation can cause a qubit to lose its quantum state, its superposition or entanglement. That introduces errors into the calculation.
Okay, so the calculations can just go wrong.
They can, yes. This noise significantly limits the complexity and duration of computations we can reliably run today. You can only run algorithms that are relatively short and shallow before the noise overwhelms the signal.
I see.
So we're all actively working towards fault-tolerant machines. That's the holy grail right now. Machines where error correction is so robust that we can run very long, very complex calculations reliably.
And you mentioned there's progress there, maybe needing fewer qubits than thought.
There's some really promising recent research, yeah.
Yeah.
Better error-correcting codes and techniques suggest we might need fewer physical qubits to create one stable logical qubit for tasks like breaking encryption than some of the earlier, more pessimistic estimates. So progress is definitely being made.
Okay, that leads us right back to that error correction puzzle. You mentioned we can't just copy qubits to make backups because of the no cloning theorem.
Right.
So with these incredibly sensitive, noisy systems, how on earth do we even begin to correct errors without disturbing the very quantum information we're trying to protect? It sounds impossible.
It does sound impossible, but that's the ingenious puzzle that quantum error correction solves. Since you can't just peek at equbit directly to see if it's wrong, because that would collapse it.
Right, the measurement problem.
Exactly. You have to use a much more subtle approach. The core idea is redundancy, but done in a very clever quantum way. We encode a single piece of quantum information, what we call a logical qubit. Not in one physical qubit, but across a network of several entangled physical qubits.
Okay, so you're spreading the information out.
Precisely. You spread it out. These special codes and circuit designs are built in such a way that if one or even a few of those physical qubits get corrupted by noise, the other entangled qubits in that network still hold enough collective information to let you figure out what kind of error occurred and where, and then correct it without ever directly measuring the original logical qubit's state.
Wow. Okay, how does that work without measuring?
It uses cleverly designed measurements, often involving extra ancilla qubits. These measurements don't tell you the state of the data qubits, like is it 0 or 1, but they tell you about relationships between them, or parity checks. They basically detect the symptom of an error, like has a bit flip happened here, or has a phase flip happened there.
Ah, okay, so you detect the error type and location, not the data itself.
Exactly. And once you know the error syndrome, the code tells you how to apply a corrective operation, like a specific quantum gate, to fix it. It's all about trading a significant amount of hardware resources, using many physical qubits and complex operations for the reliability of one stable logical qubit. That's the path to fault tolerance.
That is a truly elegant solution to a massive challenge. Okay, so with all this progress, let's circle back to that term quantum supremacy or quantum advantage that we've heard. Did a quantum computer actually achieve something truly unbeatable by classical machines? What's the story there?
Yeah, it's a key milestone and also a source of some fascinating debate. So quantum supremacy, or sometimes people prefer quantum advantage, now refers to the moment when a quantum computer performs a specific calculation that's practically impossible for even the fastest classical supercomputer to do in any reasonable amount of time. In 2019, Google's Sycamore processor famously tackled a particular task, essentially sampling the output of a random quantum circuit. They claimed it did it in minutes, whereas they estimated it would take the most powerful classical supercomputer at the time, something like thousands of years.
Thousands of years, that sounds pretty supreme.
It does. But then, as you probably remember, there was some pushback.
Right, IBM and others argued that maybe with better classical algorithms or more memory, a classical computer could do it much faster than Google estimated.
Exactly. Researchers developed some clever new classical algorithms that significantly reduced the estimated time for a classical machine to simulate that specific problem. The goalposts definitely moved.
So was it supremacy or not?
Well, the debate highlighted that the definition of supremacy on a specific benchmark task can be a moving target as classical methods improve. However, the core truth remains, I think. Quantum processors have demonstrated they can already outpace classical computers on certain problems, especially those specifically designed to leverage quantum effects, like simulating quantum systems.
Okay, so maybe not that one specific problem, but the capability is there for some tasks.
Precisely. For instance, D-Wave, which builds quantum annealers, a slightly different type of quantum computer, showed they could simulate complex magnetic materials in about 20 minutes. A task estimated to take traditional supercomputers nearly 1 million years using comparable methods.
It's 1 billion years.
So for you, our listener, the takeaway isn't really about one single supremacy event being the final word. It's more about recognizing that this technology is demonstrably real, it's rapidly advancing, and it's already showing unique capabilities on certain kinds of hard problems. The advantage is real, even if the specific bar keeps shifting.
That makes sense. This is where it gets truly interesting for you, our listener. Beyond the scientific milestones in the hardware race, what industries will quantum computing fundamentally reshape, potentially in the next decade or so? Where will its unique power really shine?
Oh, the potential applications are vast, really. Precisely because quantum computers can tackle problems involving immense complexity. One of the most talked about and potentially earliest impacts will likely be in drug discovery and material science.
How so?
Imagine being able to simulate molecular interactions with unprecedented accuracy. Classical computers struggle with this because molecules are inherently quantum mechanical systems.
Right.
Quantum computers could allow us to design new drugs molecule by molecule, predict their efficacy and side effects far faster, or engineer novel materials with specific properties. Catalysts for cleaner energy, better batteries, superconductors, the list goes on. Pharma companies are already exploring quantum simulations for this very reason, aiming to dramatically shorten those long discovery cycles.
That alone sounds revolutionary. What about something like cybersecurity? We keep coming back to Shor's algorithm breaking encryption. That sounds like a huge downside, but maybe there's an upside too.
It's definitely a double-edged sword. quantum computers could indeed break many of today's widely used public key encryption standards, like RSA and ECC, creating a massive global security challenge. We need to take that very seriously.
Okay.
But this threat is also driving the development of post-quantum cryptography, or PQC. These are new encryption methods, based on different mathematical problems believed to be hard for both classical and quantum computers. It's a whole new field, essentially creating quantum-resistant security. So it's an arms race, yes, but one where the defensive solutions are already being developed and standardized. NIST in the US is leading a big effort here.
So breaking codes, but also making new, better codes.
Exactly. And beyond security, quantum computing offers incredible potential for optimization problems.
Optimization, like finding the best route.
Precisely that kind of thing, but on a massive scale. Think about optimizing complex logistics for shipping companies, finding the most efficient flight scheduling for airlines, managing financial portfolios to maximize return while minimizing risk, or optimizing supply chains for manufacturers. These are often incredibly complex problems with billions of possibilities.
Too many for classical computers to check everything.
Right. Quantum algorithms like quantum annealing or specific optimization algorithms might find better solutions much faster. Companies like Airbus and Volkswagen have already run pilot projects testing quantum algorithms for things like more efficient aircraft loading or optimizing traffic flow.
It sounds like it could touch almost any industry dealing with complex systems.
Pretty much.
Yeah.
Finance, AI, and machine learning, chemistry, logistics. The potential impact is really broad.
Okay, so what does this all mean for the near future then? Will we all have quantum computers on our desks next year? Probably not, right? And maybe more importantly, what are some of the biggest misconceptions we need to clear up for you, our listener?
Yeah, definitely not on our desks next year. We're certainly not at the point where quantum computers replace your laptop or smartphone. It's much better to think of it like the early days of classical computing, maybe back in the 1970s.
Okay, mainframes in big rooms.
Exactly. A nascent field, absolutely brimming with potential, but still needing lots of development. The roadmap for getting to those fault-tolerant logical qubits is aggressive. IBM and others are aiming for significant milestones before 2030.
But still a ways off for everyday use.
For direct everyday use, yes. But accessibility is key here, and it's improving rapidly. You won't need a specialized lab with giant refrigerators yourself. Quantum computing is already coming to the cloud.
Through services like Amazon Bracket, Microsoft Azure Quantum, IBM Quantum Experience you mentioned.
Exactly those. They provide access to researchers, developers, and businesses who want to start experimenting and building quantum algorithms now, running them on real hardware remotely. That's how most people will interact with quantum computing for the foreseeable future.
So it's not about replacing classical computing, is it? It's more about augmenting it for specific, incredibly hard problems. That seems like a key point.
That is probably the most important takeaway, and it leads right into the biggest misconception people have, that quantum computers are just faster, super-duper classical computers.
Right. Just a speed boost?
No, they are fundamentally different. They operate on different principles to solve a different class of problems. Your classical computer, your phone, they will still be king for browsing the web, playing games, writing documents, spreadsheets, all the things they do well now.
Okay, so they're not a universal accelerator.
Not at all. Another common misbelief tied to the encryption thing is that quantum computers will instantly break all encryption everywhere overnight.
The quantum apocalypse.
Right. That's also not true. Firstly, it requires large, fault-tolerant machines, which we don't have yet. Secondly, as we discussed, post-quantum cryptography is already being developed and deployed. It will likely be a gradual transition and an ongoing arms race, not an instant switch flip.
So maybe if classical computers are like highways fast, reliable, and direct for most destinations we need to reach daily, quantum computers are more like specialized wormholes. They might get you to certain very specific, far-off, incredibly difficult destinations almost instantly, but only for those kinds of problems where their unique physics offers a massive advantage.
It's a perfect analogy, actually. Wormholes for computation. They excel precisely where classical highways get gridlocked in exploring those vast quantum possibility spaces, accurately simulating quantum systems, and cracking certain types of complex optimization and factoring problems.
Okay. My big takeaway then for you, our listener, is really this. You don't need a PhD in theoretical physics to start understanding the potential impact of quantum computing.
Absolutely not.
This technology isn't some distant dream anymore. It's rapidly evolving, it's becoming more accessible via the cloud, and it's already shaping strategic decisions being made today in businesses, governments, and scientific research across the globe. It's a field demanding new ways of thinking, new algorithms, new skills, and its implications are truly profound.
The future of computation isn't just about going faster down the same road. It's about opening up entirely new landscapes. It's fundamentally different.
So here's where it gets truly interesting. As you consider this unfolding revolution, how might the unique capabilities of quantum computing, this incredible parallelism through superposition, this spooky action at a distance, through entanglement, how might those fundamentally reshape your industry or your area of interest, or even just a problem you care about? How might it shift your perspective on what's computationally possible? Could it open up entirely new questions or opportunities that maybe you hadn't even considered before? This has been our deep dive into the fascinating world of quantum computing. We really hope it helps you understand, navigate, and perhaps even start thinking about how to harness the revolution that's truly just gathering pace. Stay curious, think quantum, and keep building the future.
1, 2,